Hello, I am Wit from Data Lab's Machine Learning Development Team. Today, Wit Koui and Saito will talk about a distributed computing library for large-scale machine learning applications. I would like to introduce some of our large-scale machine learning projects. There are 3 machine learning applications in line: classification, recommendation, and representation learning. I will not go into details on each one, but all of them utilize large-scale machine learning. To give you an idea of the scale, the number of active and inactive users are over 800 million globally. Number of items for the largest sticker package is over 10 million packages. And lastly, we run over 100 scheduled machine learning jobs. There are many methodologies of machine learning. However, the deep model using GPU is currently the most popular. However, there were a number of technical challenges when performing large-scale learning with deep models utilizing GPU. In this presentation, I will show you the libraries that we have developed in order to overcome such challenges. This session consists of 3 parts. Part 1 is about ghee, which is a library to process large-scale data in a distributed manner. Second is ghee-models. This is a library to reuse and manage the models developed with ghee. Third is Cumin, which is to validate the reproducibility when developing on machine learning datasets. I will be explaining the first part. Here is the agenda. I will start by introducing the motivation of ghee development, followed by ghee introduction and ghee implementation. Starting with the motivation. As explained earlier, the main model used for machine learning is the deep model. This picture shows the configuration and procedure to learn the model based on GPU on large-scale data. Left-hand side, we have general-purpose Hadoop cluster. Right-hand side shows the Kubernetes clusters for machine learning. We were developing models following the procedures 1 through 4. First, we build the dataset using the Spark cluster, and we copy the developed dataset to the computation cluster. And number 3, after preparing the GPU machine on the computation cluster, model analysis and offline evaluation is performed. And finally, we write back the models and inferred results from the computational cluster to the Hadoop cluster. This is a simple workflow, but once the amount of data reached terabyte level, we faced many issues. I will now explain the issues. The main problem was data skew and duplication. This drawing shows the initial configuration to learn the model in a distributed manner. The training data was delivered beforehand from the Hadoop cluster. The ideal method is for each GPU card to process learning data uniformly, but that was very difficult to ensure. It was because even if the same data was distributed to each GPU, the sampling performed by each GPU caused data skew, which decreased the accuracy of the learning. As for data duplication, if grid search or parameter search is performed, many of such configurations will be created, which will consume a large amount of network bandwidth and storage. As for resource management, up till now, machine learning engineers manually acquired and released the GPU machines. If a GPU machine is occupied for a long time, there will be a shortage of GPU machines. About GPU utilization, if processing and sampling are implemented in the GPU card in a naive manner, the GPU utilization will go down because of CPU I/O process overhead. Based on such challenges, For us to be able to focus on GPU model development, we wanted to implement a library or framework with the following features. First is data transfer. We wanted a stream instead of copy the data from the Hadoop main storage. Second is ease of use, meaning a library or interface that hides the infrastructure details. Third is distributed training. This is a feature to be able to perform distributing training easily and to be able to uniformly send training data to the GPU workers. For this, we considered using existing Spark and Dask. Although Spark was easy to use, the data transfer speed did not meet our needs. As for Dask, the data transfer speed was good, but we thought it was still too difficult to use. That's why we decided to develop our own library called Ghee, focusing both ease of use and data transfer speed. So that was the background. Now I will explain Ghee itself. Ghee is a Python library to process data in a distributed manner, and the main application is machine learning. To use Ghee, the user must specify the following. 1. Input and output specification, such as file parts of Hadoop cluster or Kafka's consumer topic. 2. Execution environment. For example, the CPU, memory, and Docker image that the user wants to use. Third is the most important, the Python program that the user wants to execute, such as pre-processing function and training loops. By specifying these, the user can run the machine learning application. Ghee will handle the transfer of data and Kubernetes management in the backend. So machine learning engineers can just focus on model development. Now, I will explain to you the execution of programs written in Ghee. First, boot the Kubernetes pod in the specified execution environment. In this case, it's pre-process, predict, train, and post-process. So 3 pods are set up. The specified input data is read in and is sent to the pod as a stream. 3. Using the specified user program, the data is processed. In this case, what comes in as input data will be pre-processed. Finally, the processed data will be sent to the next stage as a stream. In this case, the pre-processed data will be sent as input for the next stage, train. This flow will be repeated, and at the end, if there is no next step, the results can be written into the output storage. Next, I will show you the source code program written in Ghee. But before that, this is a general training program written in PyTorch. As you can see in the middle, the dataset is usually read from the disk. The next slide shows how this is written in Ghee. This is a sample of learning using a program written in Ghee. Please focus on the bottom 3 lines. By specifying the input data, pre-processing function, and training loop, that is train function here, the Ghee program will be run. The pre-process is defined at the very top, but it simply creates the training batch. The training loop in the middle is more or less the same as the general PyTorch program. The biggest difference is when the dataset is created in the middle, what comes in as a result of pre-processing will be processed instead of reading from disk. In case of large datasets, I will explain about scaling. When creating tasks in the middle, it is possible to configure each pod. In this case, CPU memory, replica, or Docker image can be configured. The data resources to be used can be easily adjusted depending on the amount of data. That was introduction to ghee. Now I will explain about the ghee implementation in the backend. The most complicated part is data transfer. The diagram on the right shows the data flow from CPU pod to preprocess, CPU to GPU pod. We use push-pull mechanism of 0MQ for inter-pod data transfer. Line has used 0MQ in the past, so we decided to use it because of its speed and stability. We also used a module called Transfer Manager to manage the complicated multiple push and pull. Last, for parallel processing, all stages are realized through MPI. By doing this, we can naturally support parallel learning with MPI. For example, Horovod. I will now explain about remote execution of user calls. Basically, the Python program written by the user will be executed sending it to Kubernetes pod using Cloud Pickle. About execution on Kubernetes, we internally developed another proprietary library called Sweeney to abstract the setting of Kubernetes. Other than execution on the pod, Sweeney also has pod lifecycle management and health check features. And the bottom diagram is the execution stack. Sweeney agent on the Kubernetes pod manages the state of the pod. MPI run and user code is executed on top of that. Lastly, for the ghee design, we focused on speed and ease of use. Here we compared ghee against Dask. Factorization machine method was used on movie lens data. Training is performed with one GPU, but the pre-processing is done on 16 CPUs in parallel. The weight of the pre-process can be adjusted with the parameter n. The results can be seen on the graph on the right. The vertical axis is processing time. Green is ghee time, blue is Dask time. As for line of code to implement this experiment, ghee only needed half the amount of code compared to Dask. And the difference mainly came from Kubernetes pod state management and data read and write. So ghee time is shorter than that of Dask. Ghee is very good at doing this, so we were able to implement this very easily. That was all about ghee. Thank you very much for listening. I am Koui. I will talk about the ghee models that perform model management. The agenda is ghee models introduction, followed by application of graph convolutional networks. I will start with ghee models. Ghee models is a library that provides a collection of machine learning models based on ghee. By using MLflow, it provides a standard way to manage the models. Ghee models have three characteristics. First, models and model parameters can be managed centrally with MLflow, leading to high reproducibility. And by offering highly abstract API, it is very reusable. And lastly, through machine learning task and data formatting, the pre-process, the post-process training process can be encapsulated internally. This makes it very extensible. I will now tell you about the concrete implementation and design. This picture is the ghee execution process, which was shown previously. Based on ghee, we implemented ready-for-use, pre-process, train, predict, and post-process functions into ghee models. We also put in a data checker to check if the data format is correct, as well as a config loader. To manage the model, we also included MLflow. To make it easier to understand, I will show you an example code. This is a code that needs to be implemented at a minimum when you want to pass a new model. Train preprocess is the preprocess function for the training data. Predict preprocess is the preprocessing function for prediction data. Train is the training function. Predict is prediction function. Postprocess is a postprocess function only used for predict function. I will give an example code for image classification. To show you the actual flow, the train preprocess function preprocesses the image that has been read in and generates the page. Ghee takes care of transferring the data to each pod. If the preprocess is heavy, you can just increase the number of pods and processes. The train function receives the data and trains the model. The predict process function is very similar to the train preprocess function. It creates ID and the image page. Predict function will read in the train model from MLflow and perform the prediction. In the background, Ghee will organize the predicted pages into a partition store into a storage. This is the definition of input format. Data checker will use this definition to check the data. This code is an example of config. In the data segment, you can specify the data path. In the model segment, the model parameter can be specified. In the Ghee segment, the Ghee environment can be specified. For example, the number of pre-processing for each pod. And the Kubernetes segment, the cluster setting can be configured. For example, number of pod and memory size. Currently, we have many models for various tasks. DNN for classification, models for natural language processing, image processing, and recommender models. Next, I will talk about application of graph convolutional networks. Line has a large number of user logs coming from various services, and those logs can be described as a graph. From the graph, using feature learning, we intend to acquire a multi-purpose dense vector that can be used for node labeling. The dense vectors that are generated can be used in many places such as recommender, segments prediction, and user-to-user lookalike engine. As for the scale of the data, it can be adapted to more than 15 services. It can predict more than 800 million users and more than 1.5 million graph nodes. To have this amount of graph data, distributed processing is essential, and we were able to solve this with Ghee. This is a model architecture diagram. Below, the model information on adjacent nodes is gathered and density vector between the nodes are generated. On top of the model, wide, deep layers are applied and the final density vector is generated. The loss used in cross entropy with negative sampling. BPR loss, focal, and arc phase loss are also provided. Since it is too costly to train the models with all the data every day, incremental learning was applied. When a new node is added, the model structure will also be updated dynamically. This code is part of graph convolutional network implementation. Thanks to Ghee, the computation part of the graph can be distributed easily. Pre-process function samples the adjacent nodes and transfers the smaller subgraph to the GPU. The train function receives the graph data and trains the model. 27 models are trained on a daily basis. To verify the accuracy of the generated dense vector, we test with user segment prediction task. Input data to Spark DNN is user's historical ID. The historical ID is converted within the model. The input data of dense DNN is the user's DEM vector. As a result, even if the user's dense vector is converted in the feature training, there was no significant loss in the information held by the dense vector. Conversely, the accuracy of user segment prediction was high. And since the input became the dense vector, we were able to reduce the model size. The time needed to train the model also decreased. That was all from me. Thank you for listening. I'm Saito. In Part 3, we will introduce you to Cumin, which is a library to manage the data generation methodologies. First, the motivation. We offer lots of recommendations to line services. Based on these recommendations, we generate data using lots of tables. In order to acquire appropriate training data, we set features for each table, and you also need to extract the noise. Many machine learning engineers, when creating recommendations, were doing the necessary setting with their own formats. That meant the setting method was different for each recommendation. In some cases, the filter conditions were the parameters, and in other cases, the settings were written directly in the query. On top of that, when generating the dataset, there are other tasks that need to be done, such as routine data sanity checks, such as Hive partition check. Since these similar routines were implemented differently for each recommendation, the code was not very readable. There were also problems in the experiment stage. The data was not reproducible in the experiments. The machine learning engineers tend to fine-tune not only model hyperparameters, but also filter conditions when generating the training dataset. In the ghee-models, the hyperparameters that were used in the training is remaining in the ML flow, but the conditions used for data generation is gone. Therefore, the features when tested with different data is not present. So in some cases, the tests weren't reproducible. I will now explain to you about Cumin. Cumin offers a format to describe the tables, columns, filter conditions, and fixed processes that were used. It is declared basically as a Python data class, and the setting is described in there. Through this, we were able to standardize the machine learning settings. We can also set the filter condition here. We can record the changes in conditions during the experiment, so the test can be reproducible. Next is how to use Cumin. Basically, no special process is needed to use Cumin. You can just start the Cumin process just like starting a Spark session. Using only this description, you can use Spark in the back end and access the tables that were set using Spark, just like before. Also, if there are items to check the number of data records in the setting, the validation will run automatically and a warning will be issued if there's any problem. I will also explain some other features. First is reading and writing the setting from the YAML file. This is used to receive the input and output paths from other components. Next is adjusting the output file size. When pre-processing with CPU in Ghee, unless the files are broken down appropriately based on the size of the data, the efficiency of data transfer will decline. And if a large number of small files are generated there will be too much load on the HDFS. Cumin automatically breaks down each file so that one file becomes the size of a block. By this, the problem can be avoided. Next is about implementation. Basically, the implementation hooking to the standard Spark function. When using Cumin, it is necessary to read in the settings before Spark starts. Thus, by the time Spark starts, you know the table, column partition, and filter conditions that are used. By utilizing this, while you usually need to do the variations after starting Spark, this can happen simultaneously as the Spark starts. Through this, the validation will run automatically without the user having to write the routine process. By writing out part of the output data by hooking the functions written into HDFS, the overall file size will be estimated. By doing repartitioning before the writing, the file size is optimized. Finally, I will explain about one usage of Cumin. First, you set the table needed to generate training data with Cumin. You can also describe the filter conditions here so you can record the conditions in which the data was generated. Then we feed the data created by Cumin into ghee-models. The data used for training will be stored in the ML flow within ghee-models. Through this, Cumin ensures the reproducibility of data generation, while ghee-models ensures the reproducibility of the models themselves. Now I will summarize the session. Ghee is a library to easily handle large-scale data. It also encapsulates Kubernetes pod management. By doing simple setting, the user is able to perform model training efficiently using CPU for pre-processing and multiple GPU nodes. ghee-models is a library to manage the models. Based on ghee, models that show high accuracy can be registered. This makes it possible to reuse same models without re-implementing. By using a common interface multiple, models can be evaluated on the same dataset. As a result, we are now able to offer recommendations more quickly to the products. Cumin offers the setting method for generating training data. By explicitly describing the filter conditions, data reproducibility can be ensured. By combining these while handling large-scale data efficiency, it is possible to perform reproducible experiments. Future work. In ghee-models, it is easy to register new models. We will incorporate newer models that have higher accuracy. We will also register and reuse loss functions that can also be registered on ghee. In Cumin, we plan to support more data sources. Currently, Spark and HDFS are mainly used. In the future, we also want to support Kafka. That ends my presentation. Thank you very much.